the current that is induced because of this voltage, the current that is induced wants to basically, it wants to minimize how much free stuff you get. As this leaves, is the magnetic flux increasing or decreasing?
Decreasing.
Why?
No longer there. Nothing's like fighting it. Nothing's trying to minimize the change.
Well, okay, there's two pieces to it. All right, so before we get to that, let's drop back. When it's inside completely, how is the magnetic flux changing as it moves completely within?
As it's moving inward, it's increasing. The magnetic flux is increasing as the wire's moving in.
All right, so if we go back to our definition of magnetic flux, so if it's increasing, is the area is increasing or the magnetic field's increasing? So when this thing is here completely inside and here completely inside, why is the magnetic field increasing? It's supposed to be a uniform magnetic field inside this. So the magnetic flux is not changing once it's completely inside. There's no current running through this wire. As it starts to leave, I'm going from a magnetic flux to, well, what's the magnetic flux once it's completely out? Yeah. So as I go from inside, so as I transition, is my magnetic flux increasing or decreasing?
Decreasing.
Say it again.
Decreasing.
Okay, decreasing, I think that's what I heard.
Yes.
So the current that's induced says, uh-oh, magnetic flux is decreasing, we gotta change that. We don't want to help them. So so as it leaves, the induced current will be counterclockwise in order to create a magnetic field in the same direction as this one, because it wants to fight the change. So we get a current flowing as it goes in clockwise, 0, and then counterclockwise, and then 0 again. Questions before we take it one step further? I have a wire here. It is one piece of wire. It is bent at 2 spots as indicated. I have a magnetic field. Why? These are all supposed to be dots coming out. There's no real noticeable, the magnetic flux really doesn't have much meaning here because I don't have a closed loop. So let's close it. What I'm going to do is I'm going to add another wire sitting across it. So right now I've got this bent purple wire and I've got a red wire sitting on top. They are in contact. I do have a complete circuit now. So we can actually figure out what the magnetic flux is. Let's stick numbers in to start with, and then we'll go to letters. So let's make this 4 meters. We'll make the magnetic field is uniform of 7 Tesla, and we'll make this, I'm gonna call this the length, I'm gonna call this the width. The length is 5 meters. That's a 5 there. What is the magnetic flux through that circuit?
Webers?
Yep. As I move the wire, we'll call this basically the movable wire. As I move the red wire out farther away from the parallel side of the purple wire. So as I move this way at some speed v, we'll just say 3 meters per second. I'm not using 3 yet. All right. I'm approaching my Princess Bride reference. Who has not seen Princess Bride? I should have said this at the beginning of the course. I do expect you to have watched Princess Bride at some point, just because you're a human being. Or if you don't watch it, I question whether you are human. All right, so that's moving out 3 meters per second. Is my magnetic flux increasing or decreasing?
Increasing.
Therefore, which way will the current flow through my loop here? Clockwise or counterclockwise?
Clockwise.
So if this is increasing, I want to decrease the flux. So if it flows clockwise, it creates a magnetic field into the board, so correct. Let's actually figure out how much it is. All right, so I know that actually, let's find voltage. My voltage is going to be change in my magnetic flux over change in time. So let's just crank through it hardcore. So after 1 second, my width here is now 7 meters. So that's my initial magnetic flux. What's my final magnetic flux if I'm concerned with 1 second later?
Webers?
So the voltage that is induced is, well, my change in magnetic flux is 245 Webers minus 140 Webers divided by 1 second, and end up with 105 Webers per second, which is the same as what? What is a Weber per second? The single unit. Yes. Did you get that?
I just know the SI unit for change in potential.
Yeah. Yeah. We're finding a voltage here, so it's volts. So 105 volts. Now, I can't tell you what the current is that is induced because I don't know the resistance, but let's throw a resistor in here. And what number have I not used yet? I haven't used 2 yet, so let's make it a 2 ohm resistor. What will the current be? weeks ago, you would have nailed this.
It's gonna be 105 divided by 2, right?
Yeah. So if you like fractions, 105 seconds, amperes, or 52.5. That's a huge current, but then again, we're dealing with a huge magnetic field here. All right, questions to hear before we throw letters into it and come up with a formula? All right, let's do some letters. And hopefully we come up with the exact same answer. My change in magnetic flux. I know magnetic flux is just, not the eraser. Magnetic flux, that would be the change in B dot A over delta T. I got a dot product here, but I'm gonna go ahead and define my area vector to be in the same direction as the magnetic field. It's just the or if magnetic field's at a jaunty tilt, we just care about the, if magnetic field's at an angle, I just care about the part that's perpendicular to the surface. So, but I'm going to go ahead and assume the magnetic field is constant, so that's just B times delta, change in the area over change in time. My area is just length times width. So that's B times the change in length times width over time. Myself some room here. Well, my length isn't changing at all. So that's equal to B times L times delta change in width over change in time. And what's change in width over change in time in this context?
Velocity?
Or speed.
Speed.
So we end up with BLD. Now, I've just introduced a new symbol for this context. Actually, we've dealt with this. We've dealt with EMF before, didn't we? Or you have seen it in a video at least. What was that?
I think we've seen it a little bit.
Okay. This is an epsilon. And it represents EMF. And as of now, what does EMF stand for?
Electromagnetic field.
No.
Electromotive force.
That's how it started. But what does it stand for now?
Nothing.
Oh, I would say it stands for EMF, but it's not pronounced EMF. It is, you still say EMF. Historically, electromotive force is what it was, but then they realized it's not a force, it's a voltage. It's an ideal voltage. If I have a battery, a 12-volt battery, its EMF probably somewhere around 12 volts. When I actually hook it up to a circuit, I have current flowing, and part of that current is flowing within the battery itself. And the battery has resistance. And so the actual voltage from a 12-volt battery is going to be a little bit less than 12 volts because of internal resistance. If it's an ideal battery and there's no internal resistance, then the voltage of the EMF would be the same. But it's, you can think of the EMF as just an ideal voltage. But this is known as the motional EMF, and not emotional, motional. So if I have some length of wire and I drop it through a magnetic field, this is the voltage that is induced, the EMF that's induced, and then from that, if you know resistance, you can figure out the current. And this is the Princess Bride reference. For those who have seen it, when, potential spoilers here, at one point, the scene with Billy Crystal, and they're trying to figure out what Wesley said, and what Billy Crystal heard was not true love, but heard Deblev. Deblev. Although unfortunately, Billy Crystal's character did not connect it with emotional EMF, because that would have been really convenient. All right, so what this is saying is that I don't need really a circuit in order to get a current flow. That if I take a wire, and let's say I have a magnetic field that's going out of the board here, and I just drop the wire in that magnetic field, which way will the current flow? Well, if I know the speed, I know the length, and I know the magnetic field, I can calculate what the potential difference is at that moment. However, as I drop this, it will create again, charges will flow. And which way will the current flow? You were pointing it that way?
Yes.
How'd you get that?
Putting it, or that's coming out of the board, so my thumb's pointing to the right. Or like,
You're doing the book method? Which right-hand rule are you using?
I thought I was using yours.
Oh. All right, so as it falls, if the current's flowing that way, now let's run with that idea. So if current is flowing this way, which way will the induced current be?
To the left.
Oh, sorry. If the current's flowing that way, which way will the magnetic field it creates be?
Out of the board.
Where? It's circular, so it's going out someplace and in another place.
Oh, coming out at the top and in at the bottom.
All right, so it's coming out at the top and in at the bottom. So where will the weaker magnetic field be? Right, okay. And wires tend to get forced in the direction of the weaker magnetic field. So if you drop this thing would go even faster. And again, weaponized applications right there. But that's not gonna happen. Current's gonna flow the other way. It doesn't want to give you free energy. Current's gonna flow that way so that the magnetic field gets boosted below it and weakened above it. Or from the point of view of, if I have a proton that's going down with a magnetic field coming out, that's the direction of the positive charge flow, magnetic field is coming out, the force of the proton would be off to your left, in other words, this way. And connecting with something we did earlier, as it falls and I have a current flowing this way, I'm gonna start getting positive charges building up on this side and negative charges building up on that side, which creates a secondary electric field or potential difference or potential difference. But I'll have an electric field going in that direction, which will sort of make electrons want to go this way. So I've got, again, two competing forces here. I got this force from the charges trying to make electrons go this way, and then I have a force from the magnetic field trying to make electrons go the other way. And so there will be current until those balance out. One more point, and then I'm going to hand stuff back. The four equations that I wrote over here, I had Gauss's law of electricity, Gauss's law of magnetism, Ampere's law, and Faraday-Lentz's law. That is almost all of what are referred to as Maxwell's equations. James Clerk Maxwell comes in, he adds one extra bit to Ampere's law. So some people refer to Ampere-Maxwell's law or Ampere's law with Maxwell's correction, but there's one more term that's missing. Maxwell figures it out, and once he does that, we can then derive the speed of an electromagnetic wave. And that is the point in which we realized, or we humans, physicists realized, that the whole idea of electric fields and magnetic fields was not just a mathematical convenience. There's actually there is a physical nature to it. Because there was an 80-year period, probably not that much, 60-year period, where they weren't sure if electric fields and magnetic fields really existed. Let me hand stuff back. I got so close to completing everything for this class. At this point, there are two equipotential lines of electric field labs I haven't done. That's Daniel's and Sean's. The others are done. I haven't recorded those grades yet in Blackboard, but I've graded everyone else's and it in. So first, the equipotential. Oh wait, no, it wasn't Sean because I have yours right here. It was Daniel and Gina. Gina was the other one. Conceptual question, lab activity. That's that one. One piece of paper. And oops. Oh, and again, before I flash the grade.